So this is my 514 design project, and I'm working on this oscillator, and this is my first draft, and we're trying to see if it works or not by running the transient simulation. It does satisfy the frequency stability condition. We saw that using the Cauchy-Riemann condition in the S parameter simulation. So yeah. So here when I run the transient simulation and I plot V out, what we see is that we get some noisy signal at femtovolts, which is bad. So now how to fix this? So now for fixing it, what we are first going to find out is that if the conditions for starting up are being satisfied or not. And for that what we need is we go to this simulation harmonic balance palette, and we choose this OSC port 2, and we place it here at the collector or the output terminal of our oscillator, and then yeah, that should be the connection. You can also place it here, but yeah, I'm starting by placing it here. And this OSC port 2 is for the differential oscillator, but I have a single output oscillator, so you'll be simply grounding the differential terms. And now, so this also needs a frequency plan, you can see here. And now I'll put a frequency plan. You can just go to this palette, select a frequency plan, and the frequency plan you want to choose. So my design frequency is 23.5 gigahertz. So I'm going to start with, let's say, well, I don't know, like 15 gigahertz to 35 gigahertz. Right. And then the number of points. Oh yeah, so this should be 9, correct. And then the number of points, I'm setting it to like 101. You add this, you read the old one out. Oh, okay, so this is correct. And the frequency plan, let's call it small signal or SS. Okay. And now we're going to call that frequency plan here. I want to run a small signal, and the frequency plan, we named it as SS. Okay, you can run it. Wait, why is this showing some error? So here we are all set for the small signal simulation. So first of all, I'm going to deactivate this transient model because I want the simulation time to be very small, and I do this and here. Now at this screen, what I'm going to plot is the dB magnitude, the magnitude of the loop gain in dB, and yeah, so we're going to plot the magnitude and phase of the loop gain. Okay, so here, yeah, so this is the phase and the magnitude of the loop gain. Now here we see what we want. The condition for this to oscillate is that where the phase is crossing the 0, the loop gain should be greater than 0. And here we see that the loop gain is not greater than 0. In fact, it is close to like 0.1 something, negative 0.1 something. So what this tells is that our conditions for oscillation are not there, and this is never going to oscillate. And now what we need to do is we need to reduce some loss in the design. Now what we're going to do to reduce the loss is I'm going to short out these resistors in the feedback and the termination. Now remember, by shorting these resistors, the frequency at which this is going to oscillate will change, but at least we'll see that if it is going to oscillate or not. By doing the later steps of adding non-ideal pads and components, we can kind of tune the parameters and anyways remove these resistors if it oscillates at this step. So now if I rerun this simulation, now again these are again the results, and here you see that at now the phase 0 crossing is happening here, and we have a gain which is greater than 0, but the frequency has now shifted to, let's say, I don't know, about like 27, 26 something. Okay, so what this suggests is that now this is going to oscillate. So now the next step would be to run the harmonic balance simulation and exactly figure out at what frequency is it oscillating. For this, step 1 is to add a harmonic balance engine, and here the frequency that I want to do is like 25.3 gigahertz. I want to see 15 harmonics. You add this and you delete the old frequency plan. Okay, and then you go to the sweep. It's okay. Oscillator. Yeah, you have to specify nodes here. So here I have specified the collector node as VC, and this is what I'm going to look at. See. Now there's a term called node minus, because ours is a single-ended oscillator. So I'm going to leave this blank. The rest all parameters are standard. So you just press this, and we don't need this anymore, so you can delete it and connect this. Good. And now I'm going to run the simulation again. Now here what I'm going to plot is the spectrum of VC, and here we have the spectrum. Now here we see that at harmonic index 1 we have the highest gain, or the oscillator is going to oscillate at this point, and that we can find by using this. So fundamental 1 is close to about 25.08 gigahertz. So by removing these resistors, now my structure is going to oscillate at 25.08 gigahertz. Yeah, so now I'm going to run a transient simulation. So you bring in the transient block, you remove the harmonic balance block, and you run the simulation. And you plot V out, and boom. So you see that this is now oscillating, but the frequency is 25.08 gigahertz. So once this is oscillating, now you can go to further steps and tune this and bring the frequency to your design frequency. Okay, that's it. So this is the steps of designing this oscillator. Thank you.